Alright, I'm going to do the work in Mechanical Advantage Lab using simple machines. So the first thing we're going to do is the inclined plane. I have it set for 25 degrees and our load is going to be this little cart. So the cart can roll up the hill and we want to find the force needed to pull it up the hill. And the first one we're going to do is just an empty cart at 25 degrees. The next run, I'm going to add a 500 gram weight to the cart and then do it again with 500 grams added to the cart. And then we'll repeat those two at 45 degree angle. Right, now I want to measure the force it takes to pull the load up the hill. And to do that, I can drape it over the string, over the pulley, and hang a weight hanger here. And then by hanging a weight hanger, I can put weights on here until I have just enough weight to pull this thing up slowly at a constant speed. Okay. Now I don't have to go all the way up the hill. I'm trying to measure the force needed to do the work of lifting the cart up the hill. If I have too much weight on here, it will accelerate. And so I'm not only doing the work of lifting the load, I'm also increasing kinetic energy. So I don't want it to accelerate. With no acceleration, then the force pulling up the hill is equal to the weight down. And I'm measuring just the force I need to do the work of bringing this up the hill. So I don't have to go all the way up the hill. I just want to make sure that it moves slowly at a constant speed so it's not accelerating. Okay. Well, first of all, I need to know what the mass of my load is. So I have a laboratory balance here. And I put the cart on here and I can measure the mass. Okay, I got it there. So got 150 plus 2 more, so 350, 355.5675. So 355.75. So the mass of the cart is 355.75 grams. Make sure you put units. I can just put a G, small g in parentheses in the column header to represent the mass. Yeah, so right halfway between the tick marks, between the 7 and the 8.7 and 0.8, so it's 355.75 grams. Okay, so now you have to measure the cart. I'll put the cart on here. Oops, before I do that, I want to measure the distance the height. Now, the distance and the height ratio gives me the theoretical mechanical advantage. And that only depends on the angle of the tilt. It doesn't really depend on this distance and the height. So what I can do is just pick 2 marks on the board, measure the distance between those 2 marks. That will be the D. And then I measure the height of the upper mark and the height of the lower mark, and the difference in those 2 heights will be my H. So I've got 2 marks on here I'm going to measure. And I've got them right at 24.00 centimeters. So the D, 24.00 centimeters. Right. Now the height of the upper mark is 12.670. I'll write that down here. And then the height of the lower mark right at 3.00. So the difference then is 9.70. So the height is 9.70. And that's also centimeters. Okay? Then the TMA, or theoretical mechanical advantage, will be the distance divided by the height. So it'll be 24 divided by 9.7. And of course, it's centimeters over centimeters, so there's no unit associated with TMA. All right, now I've got the mass of the cart. Now I need to find out what mass I need hanging here to pull the cart up the hill slowly at a constant speed. So 50 grams is not enough. That's not quite enough. I have some small weights. But 5, we got too much. That goes by itself. I don't want it to go by itself. I need to have enough so I just give it a little push. It will move slowly at a constant speed. So I've got some 2s. Put 2. That's it, I think. No, that's too much. Try 1. I want to make sure wheels are all lined up right, so I'm not pulling it at an angle, and I want the string to be as parallel as I can, so I'm not lifting the cart up or pulling it down into the plane. I want to pull it parallel to the plane. I don't know. Okay, I think that's it. So I've got 50 for the hanger, another 100, that's 150, 152 grams. Okay, now I'm going to add 500 grams to the cart and do this again. Is that enough? Not enough. Let me get the cart lined up. It's too much. A little too much. Put 5. That. Enough. More. there. Put 2 more. One more. Okay, that's it. All right, how much do I have? 50, another 50 is 100, 200, 300, 350, 360, 365, 367, 368, 368 grams, and then the cart is now 855.75 grams. And the D and the H didn't change because I didn't change the angle. Okay, now it's important that I do the calculations before I change this, because if I made a mistake in any of my measurements and I end up with an efficiency of greater than 100%, then I know that I did something wrong, and I'd never be able to get this in exactly the same spot again. So I'm going to do the calculation. So the TMA is the distance over the height. So I do 24 divided by 9.7, and I get 2.47 for the TMA. Okay, now my AMA, I have 355.75 divided by 152 equals 2.34, and 855.75 divided by 368 is 2.33. All right, so then my efficiency, I take the AMA divided by the TMA and multiply it by 100. So 2.34 divided by 2.47 equals, and I get 94.74%. 94.74% for that one, and have 2.33 divided by 2.47 equals, we get 94.33%. So for the inclined plane, we don't have very many moving parts, so there's not very much friction. So about 95% efficiency is pretty good. Right? So remember, it's friction that really robs your efficiency in these kinds of machines. All right, so our efficiencies came out about right. So next, I'm going to move the angle up to 45 degrees. Indicator on here. And then we're going to repeat this. All right, now I've got a defective cart, so the wheels came off. So I'm going to pause the video and repair my cart. All right, I got the wheels of my cart repaired. So I moved this up to 45 degrees. Now since I changed the angle, my H is going to change. So I need to measure the height of my top mark. And now I'm at 19.90 for the upper one at 3.40. So 16.50 is the H. And still 24.00 for the D. And I can write that again for the last line too. So 16.50 centimeters for the H and 24.00 centimeters for the D. All right, now we're going to do the empty cart. This much weight. And of course, with the steeper slope, is going to have a smaller mechanical advantage. Closer. Pulley. And it's too much. 5. It's too much. 2s. Close, maybe one more. That's it. Check again. Okay, moving slowly at speeds. All right, I've got 100, 200, 250, 252, 253, 253 grams. So 50, 100, 200, 253, 253 grams. All right, now we're going to put 500 grams in the cart. Not enough. Still not enough. Still not enough. I may not have enough weights here. There. Oh, all right, just enough. Be just about it. I think that's a little too much. It goes by itself. So I take off a 10 and add a 5. And 4. That's it. Okay. Okay, there's 100, and another 2, there's 300, 4, 500, 550, 550, 20 is 570, 80, 90, 590, 600, 605, 6, 7, 8, 9, 609. 609 grams. Let me count that again. There's 50, another 50 is 100. There's another 200. There's 300, 4, 500, 550. 550 and another 50 is 600, 605, 6, 7, 8, 9, 609 grams. And so the cart again, empty cart was 355.75. And the full cart was 855.75. Okay? Let's check our efficiency. So, calculator. The TMA is the D over H, so I got 24 over 16.5. 1.45. And then we have for the empty cart, we have 355.75 divided by 253, and I get 141. 1.41. And then 1.41 divided by 1.45 equals times 100, and I get 97.24%. Then we've got 855.75 divided by 609, and we have 1.41 again. So again, 97.24%. Okay, so that's all for the incline plane. Next, I'm going to do the system of pulleys. We're going to do a 5-string pulley system and a 3-string pulley system. So I'll get that set up and we'll be back. Okay, now I've got my pulley system set up. This is my load. Right here I have 1,000 grams total, including the hanger. So this is going to be the load that I want to lift up in the air. And I want to find out how much I have to pull on this side to lift it. This is my input force side. So this is like the block and tackle that you would use to, say, move a piano up to the second floor. So I want to find out how hard I have to pull on this side in order to lift this 1,000 grams. And I have a 5-string pulley system. There's 1, 2, 3, 4, 5 strings supporting the load. So this is my input side, this is my load side. So to do that, to measure what that is, I'm going to hang some weights on this side and then put just enough on here so that when I give this a little bit of a push down, this load will move up slowly at a constant speed. So if it accelerates, then my input is not only lifting the load, it's also increasing the kinetic energy. I don't want that. I want it to move slowly at a constant speed so that the forces are balanced, and I'm only measuring the amount of force needed to lift the load. Okay, so we've got 50 for the hanger, here's 100, here's 200, 300 is too much. 320. 340 is too much, or 240, excuse me. So there's 230. That's too much, it's going by itself. 32. That looks about right. Yeah, that's still going. Look at that. That's just right. I got it pretty quickly. Okay, I've got a total, there's 50, another 50 is 100, there's 100, there's 200, 220, 230, 232. So 232 grams is all I need to lift 1,000 grams. 232 grams lifts 5,000 grams. All right, now, what about the D and H? Let me get my data sheet. I better record that. Our load mass is 1,000 grams. For both the 5-string and the 3-string. And our effort mass, what did we say? 100, 200, 20, 32. 232 grams. Okay, now what about the D and the H? Well, it turns out the theoretical mechanical advantage for the pulley system is just the number of strings that hold the load. And of course that makes sense for both the D and the H, right? Because if I want to lift this 1 meter, I have to shorten each one of the 5 strings by 1 meter, right? So I have to pull 5 meters of string through here. So 5 to 1. But let's go ahead and measure that just to see. A bit too small. So I just want to see if it moves 5 to 1. Okay, I have this at about 95. And I move this up to the 20. And it went down to 94. 91. So 91 to 95, this side moved 4 when this side moved 20. So this side moved 20 centimeters, this side moved 4 centimeters. 20 divided by 4, of course, gives me 5. So on the D and the H, the D I'm going to write 20 centimeters, and the H 5 centimeters. So 20 divided by 5, or excuse me, 4 centimeters. So the D was 20 centimeters, the H was 4 centimeters. 20 divided by 4 gives me a T and me of 5. And it actually worked. Okay, next, I want to get it down to the 3-string pulley. 3-string pulley, of course, is going to be less efficient. It's going to be less mechanical advantage. So I just unwind one pulley there, and unwind another one here. And now I have 3 strings holding my load. I need some more weights, I think. No, maybe not. I got enough. But I'm going to raise it up a little bit, make it higher, so it's easier to measure. Okay, that's too much. Not enough. too much. Close, but still too much. Oh, very close. Gonna go all the way. That's it. Do it once more. Not accelerating, very slowly, constant speed, and it just go all the way down to the floor. Okay, so I got just enough now. Alright, I can remove this. And now I want to count these. So I got 100, 200, 300, 350, plus 20 is 370, 372. So 372. So 372 grams lifted 1,000 grams with the 3-string pulley. 232 grams lifted 1,000 with the 5-string pulley. All right, now I want to check the D and the H again. And I can do that without putting all the weights on. Just need a hanger. Okay, 3 strings. Let that go to the floor, and I want to see if it goes 3 to 1. I put my meter stick, and this is at the 86, so I'm going to move this up to the 18 centimeters. And this goes down to 80. So when this side moved 18 centimeters, this went 80 to 86, or 6 centimeters. So 18 centimeters for this side, 6 centimeters for this side. So the D, I'm going to write 18 centimeters. And for the H, 6 centimeters. 18 divided by 6, of course, is 3. Okay, so now the AMAs, I just take the effort mass, or excuse me, I take the load mass, 1,000 grams, divided by the effort mass, is 232 grams, to get the AMA, and let's do that. My calculator. So 1,000 divided by 232, I get 4.31 for the AMA for the 5-string. And then divide by 5, and it gives me an efficiency of 86.21. 86.21%. And then for the 3-string, I take 1,000 divided by 372, I get 2.69. So 2.69 divided by 3, I get 89.67%. So for the 5-string, we had 86.21% for the efficiency. In the 3-string, we have a little higher efficiency, 89.67%. So why is the 3-string more efficient than the 5-string? Well, with the 5-string pulley, we have more moving parts. There's going to be more friction. So even though it's less efficient, I get a greater mechanical advantage. I was able to lift 1,000 grams with only an effort of 232 grams. So if I couldn't lift 1,000 grams by itself, well, by using the 5-string pulley, I only have to pull 232 grams to lift 1,000. So this is how you can lift that piano up in the air if you use a pulley system or a block and tackle. So the machine multiplies your force. This is the input force. The output force is the weight of the load. Okay? Now, of course, we did everything in grams. And grams, of course, is not weight. But to get the weight, I multiply by g, the acceleration due to gravity, to get the weight in force units. But I have to multiply by g for this side and multiply by g for this side, and we're only taking the ratio. And when I take the ratio of the two sides, the g divides out. So the ratio of the masses is the same as the ratio of the forces. Okay? All right, so that completes the data collection for this lab. So the rest of it is just completing the calculations and answering post-op questions. Okay, so that's it.